Hi.
All right. So
Hi.
first of all, welcome to Sockets in Ruby. Uh, last couple of weeks, I've been writing a whole bunch of socket programming, building two-way communication, writing clients and servers. And I figured this is not something Ruby programmers come across quite often. And I figured I'll give everyone like a primer of how to do socket programming in Ruby. I'll cover foundations and some design principles, and then actual code in Ruby. I'm going to go ahead and start sharing my screen, and let me know if everyone is able to see the screen.
Yeah, not yet.
Okay, how about now?
Yep.
Yep.
Hang on, which screen are you seeing? Okay, which screen is everybody able to see?
Yeah, we're able to see the Ruby socket screen.
Presentation.
Ruby sockets. All right, cool. All right, so yeah, the talk is like sockets in the Ruby world, and what I want to cover today is what the docs will tell you and some things the doc won't tell you. Most of the things I'm going to cover you can figure out based on some playing around with the docs and articles in the wild, but there are some things which are not easily understood or they're not apparent, and those are the ones I want to focus on for today. It's roughly divided into three sections: a primer on sockets, which basically just look at what sockets are, the life cycle and fundamental design principles of sockets, and then followed by the two most common socket constructs, which is servers and clients. Clients are actually very easy. Most of us have written a client in our life at least once. Whenever you're talking to an HTTP server, you're writing a client. Or HTTP communication happens over sockets, which means you've written a socket client if you've written an HTTP client. Sure, you may not have directly opened a socket and connected and done all that, but under the hoods, that's all that is happening. It's the servers where all the interesting things happen and all the design principles and all the things that we need to sort of learn or I would say trade-offs. Those are all primarily that happen on the servers, and that's where we'll mostly focus today. So the goal of this talk, or when I started writing the code that I'm going to show today, was to build a smooth two-way communication between two sort of similar entities. If you've done any kind of distributed systems, you would know like homogeneous systems where two entities are sort of the same and then they talk to each other. Server and client are slightly different from that. If you have an HTTP server or Redis server or socket server, clients initiate the connection and then the server responds to that request. And so we'll see some of both today. But the goal of the talk is also to understand some design trade-offs and what not to do, what to do, and what are some good things and what are some not so good things. So let's go ahead and dive right into the primer. The very first thing that I want to, or that comes to mind when we think about sockets, is that sockets read over network. Right? That's what they're built for, reading and writing over network. Sockets also write over the network. That's the very foundation upon which the socket programming world is built. And if you want to sort of draw analogies, then reading is akin to listening. You can't really listen unless there is someone doing the talking or something to listen to. So, which means the servers basically start listening to something, but then nothing is going to happen until somebody speaks or somebody sends a request. And so, extended the same analogy, writing is basically talking to someone. There must be someone to talk to, otherwise nothing's going to happen. But you can talk without any dependency on them. And like coming back to the internet world or the networking world, if there is a server that is available, then you can talk to it. If the server is not available, you can't talk to it. But once you have opened the connection to the server, you can just write anything, and then the server will act on it as it sees fit.
Swanand,
And so, yeah.
Sorry, can you be a bit louder? Ashwin is asking in the chat about it. Is there any issue?
Okay, I hope.
Is everybody able to hear Swanand?
Yeah, we can hear.
Yeah, yeah.
Okay. Yeah. Sorry to disturb them. Go ahead.
Okay, no problem. If anyone is not able to listen or raise hands, or if there are any questions, just feel free to interrupt and ask the questions right away. I want this to be like a free form discussion than just me reading out in some code. So if you feel like you're not able to follow anything, just interrupt and ask the question right away. I think Zoom has a thing called raise hands, and Prathamesh can watch for that and interrupt as needed. Cool. So coming back to our analogy, reading is sort of like listening, and then writing is talking to someone, and then extending the same analogy, then reading is basically what the server does, and writing is what the client does. However, this isn't strictly true. Both client and servers do both reading and writing, but it's true from a sense that clients initiate the connection, and then servers sort of respond to that connection. I think this much I'm pretty sure that all of us understand on a fundamental level that this is how socket or clients, any kind of client server communication happens. Sockets are no different. They operate on the same way. Both servers, and like I said, both servers and clients read and write. So let's look at the life cycle of the socket. This is the most important thing to understand from this entire talk. If you understand the socket lifecycle very well, there are two concepts. One I'll cover a bit later. That and lifecycle. These are the two important things to take away from this talk. If you understand these two, then I think you are all set to write or start writing socket related code. A server lifecycle starts, or in a nutshell, is like this: you create a socket, you bind it to an address, then you listen for incoming connections, then you accept incoming connections, and then you close the connection. This is strictly in order, and this is the exact sequence of things that happen. Each of these action is related to an underlying syscall that the network layer or the operating system provides. If you look at man pages, you will find syscalls for each of them, and Ruby simply bubbles them up in the API layer and offers a neat, easier layer to work with. So you basically create the socket object. You have to bind to an address. You have to listen for connections. Then you have to accept the data, and then finally you have to close the connections. Any communication with or to a socket has to follow this particular life cycle. And so the code for this is actually fairly straightforward. Is the code visible to everybody? The slide? I mean, we're not on projector, so that way we are safe.
Yeah.
All right. Cool. All right. So line by line, it's literally the life cycle on one line each. You just create a socket object. Socket is a very convenient class that Ruby offers. One note about implementation: most of the socket class is basically just a very thin wrapper over underlying syscalls. So everything that if you were writing a C program, your code would look very similar to this. The syntax will be mildly different, but the code would look very similar to this because these are just system calls that Ruby is offering an API on top of. So first up, we create a socket. There are a couple of things here like inet, stream. We'll come to all of that. We'll come to each of these line in detail later or in a short bit. Let's cover all of them. You bind it, you listen, you accept, and then you close. Literally what the words say in the life cycle, that's exactly how the code looks like. Let's jump over to the client side a little bit. Client lifecycle is very similar to that of a server, only minor differences. And this is where the notion of server and client comes in. Clients create the socket. They also bind to an address. The bind is implicit, and we're going to cover some of that later. Then they obviously have to connect to the server, and then finally, when the writing is done, the connection means writing to the server, they have to close the socket. Each of these actions is equally important, as we'll see a little later in the code. Like for example, without close, your server cannot read data effectively, etc. So each of the actions are sort of related to a design choice, and we'll see how all that ties together in a little bit. And again, just like server, all of these are system calls that the Ruby API bubbles up. If you work with net HTTP or HTTP PY or curl, they all do the same thing. And so in the same way, in client lifecycle, in sort of a descriptive way, create the socket, bind to the address, send the data, and close the connection. In many ways, clients are fairly simple. This is how the code looks like, not very different from our server. The only thing of note here is the bind. The binds are implicit. It depends on basically whether you're a server or client, how the bind happens. Okay, all right. So if you put them together, sort of in a comparison, this servers clients, they create bind, that's pretty much the same. Close is also the same, and then the difference really is in listen and accept versus connect. Okay, I see a whole bunch of messages. Is there anything for me to look at? All right. Okay, cool. So if I had to highlight, the green part is where sort of the magic happens, or all the actual data exchange happens. When the server is in accept mode, only then can the client actually send a message. Otherwise, you're going to run into some of the other error. What errors? You might have seen them quite often. If you're trying to connect the client to a server which is in these three states, the first three, create, bind, and listen, you're going to run into ERR, no, E timed out. How many people have seen this? Practically everybody who has written any kind of networking code has seen the error, right? You try to connect to a server that either is unresponsive or is not available. It's quite likely that either the server doesn't exist, or second, it is in one of these three states. Similarly, if you try to write to a socket server that has closed the connection, you're going to run into EOF errors. Now, EOF typically means end of file error. So if you know the Unix design philosophy, everything is a file. Sockets are no different. Sockets are file too. They are all bound by a file descriptor, bound to a file descriptor. And when the server or client closes a connection, an EOF event is passed on to either ends of the socket. And that is how server knows to stop reading that message. Again, more on this will come a little bit later. But this is the idea. If you connect when the server is in these three states, you get times out, and here you get end of file errors. Putting them all together, green zone is where the data exchange happens. Well, that's not all. Whatever the code we have seen so far, that really is not enough. Although in some ways, if you had to send a single message, the code could be enough. But we don't want to send a single message. There's more work to be done for us. So let's look at some of that. And the other thing I want to mention at this point is that whatever code we saw so far was a little ugly. You know, we had that pack address thing, bind, listen, all that. I mean, if you had to do all that boilerplate every single time you had to connect to a socket, why not just write C code? Why write Ruby code? And so obviously in the Ruby world, syntactic sugar exists. There are a lot of nice wrappers on top of the code that we've seen so far. And so now let's go and look into the syntactic sugar and in the context of servers and clients. So if you remember, this was our basic server code, create, bind, listen, accept, close. Let's look at each line in detail, and we'll look at what the syscalls mean and what are the design choices around each of them. Before we actually jump into any questions so far so good. Anybody not able to follow or anything? I haven't covered anything that is tricky, but still I want to pause and ask. Go ahead, Anubhav.
Yeah, so I want to know about the inet and stream. What are
Yeah,
these
we're coming to that shortly. Yeah, we are coming to that right away. All right, so inet is basically you're telling Ruby code to make an IPv4 socket. Those are called the inet sockets. There are other kinds like IPv6 sockets you could create. I'm not going to go into IPv4 and IPv6 much. The docs are pretty good on this, and that is the primary reason I'm not going to cover that. If you open the socket docs, it will tell you what kind of sockets you can create. The semantics of writing and connecting to IPv4 and v6 are slightly different, but not very different. Foundationally, they're pretty much the same. Some minor differences here and there. Practically everything we see today applies to IPv4 and IPv6 both, with some differences. Stream here basically means you're opening a TCP socket. The other being datagram, which is a UDP socket. In this talk, we'll right now only look at TCP. We're not going to cover UDP simply because I did not have enough time to prepare for both. But again, TCP and UDP are fundamentally different in the way they operate, with good reason. And so obviously the socket communication follows the design principles for each of those protocols. The fundamentals of connecting, binding, and accepting don't change. But reading and writing is a bit different in TCP world and UDP. For example, in UDP, there's no write back, whereas TCP, you have write backs, etc. So again, the Ruby object or the API mimics the underlying system calls, and then the underlying system calls mimic the underlying protocols. So to cut a long story short, we're going to look at TCP sockets today. The second line in our code looks something like this. I've just reformatted it a little bit. What we're essentially doing is server.bind, and then we are calling this obtuse looking pack sock address in method, passing it some arguments. Obviously, perceptive folks would have figured out that 4242 is the port number, and then 0.0.0, even though it may look like an IP address, it's not really an IP address. It's called a listening interface. If you've done any kind of server programming, you're probably familiar. You must have seen this. When you start a Rails server, you have the option to specify a port and a bind or a listening interface. You might also, if you have worked with Postgres or MySQL, you might have seen this, where you can tell the Postgres server what to listen to. Now, this is a bit different, or some people might have seen this, which is the Nginx server configuration. DevOps related folks or who've done server configuration would have seen this. They all mean the same thing. They're all about binding the socket or the incoming connection to a particular interface. Now, even though this looks like an IP address and is actually related to an IP address, it is not really an IP address. A server's IP is primarily about the outside world finding the server, whereas listening interface is about finding that data that has been sent to that server. 0.0.0 tells the underlying system call that anything that comes on any IP address, for any IP address, I will listen to. Anything that comes on port number 4242 is fair game for me. I will look at and respond to all of that. You could change this to say 4242 followed by 127.0.0.1, which means this socket is only going to look at connections that have come from 120 or come for 127.0.0.1. That's exactly what the Postgres config does. You may restrict, like for example, if you're on a VPC kind of setup on AWS, you can pretty much tell the RDS server that only listen for connections that are coming from these 1, 2, 3, 4 IP addresses, nothing else, which means no one else can actually send packets and communicate with that Postgres server, or in our case, that socket server. So that's what the listening interface means. The important thing to remember here is that it's not an IP address, even though it is related to an IP address. It's where you tell the socket where to find data or what data to look for. It's like a filter. 0.0.0 is pretty much like your wildcard star filter. So let's talk about ports a little bit. If we are writing our own server, we could practically choose any number of ports or any number of port. Does anyone know how many ports are available? Anyone?
65,500 and something.
Yeah, so 65535 number of ports are total available. But we can't, if you're writing R code, which is like the user space code, then not all of them are available. Ports number 1 to 1024 are what you would call as privileged ports. they're not available for your standard programs. And when I say not available, it means that you can actually listen on some of those ports with privileged access. If you like, and some of these ports are taken, like for example, 80 is the well-known HTTP port, SSH is on 22, and there are some other processes that use these ports. Normally, if you're writing a server and you're hosting a server, you should probably steer clear of these ports unless you know what you're doing. So they're in the category of privileged ports. Yeah, again, I'll reiterate, it doesn't mean that you won't be able to use these. It's just that it means that you need root access to actually listen on any of these ports. 1025 to 48,999, they're fair game to anybody. They're available and they're recommended. You can use any of these ports. Rails, for example, uses 3000. Python, Django, I think uses 8080, and so on. Tomcat used to use 8080 in the old days, and so on. And then 49,000 to 65535. These are what are called as ephemeral ports. These are also available. You can use them, but from a design perspective, it's recommended that you don't use them. And we're going to see why exactly in a minute. So let's look at a typical communication lifecycle. What happens? This is my own diagram. Don't give me a hard time with the diagram. It's a terrible diagram, but it does the job. So the client initiates the connection. Let's say the server is listening on some IP address at port 4042, like we have seen. The client sends a message on this port for this IP address because the client knows where to reach the server. You can only, TCP mandates that if you're sending a message over network, it must be sent to something. That to is usually an IP address and a port. There are other forms of messages like multiplexing and broadcast. We're not going to go into that. But for now, let's assume that the message is being sent to an IP address on a port. And so client knows beforehand. When we send an HTTP request, we know beforehand which IP address we're going to send the request to. Or when you're connecting to Redis or Postgres or whatever, you know the IP address beforehand. So the client initiates a connection and sends that message on that IP on that port. Then the server handles that message, does something. If it's Postgres or whatever Redis is going to acknowledge, and then has to send a message back to the client. Now, when the server has to send a message back to the client, in that brief moment, the server is the client and the client is the server. They've sort of exchanged the roles briefly. And again, the server needs to know which IP address and which port to send a message to. And this is where the ephemeral port comes in. So when the clients send the message in the TCP protocol, you have to mention who is sending the message as well. So the server knows where to send the message and which port. Most of the low-level client libraries will create or pick a temporary ephemeral port and then use that in the message. And then the server, when it sends back the message, it will be sent to that message. So for example, if you go back to our number of ports, let's say the Postgres server is on 5432, which is a standard for Postgres. You send a message, you send something, maybe a query, and now Postgres has to respond to that message. It will pick one of the yellow marked ports. The client will pick one of these yellow marked ports and said, okay, here is my message. And when you send the response back to me, send it on this port. And this port is bound for that short duration of that single message. And then after that, it's unbound. One thing I forgot to mention is that when we do the bind, the moment one socket binds a port, it becomes unavailable to all other sockets. That port, if you must have seen the server already in use error that comes, or port already in use error that comes because somebody is already bound to that. Okay, back to our two-way communication. So now we understood that the client included that port and IP in the message, and then server knows which port. And then so that's where the ephemeral ports come into picture. The clients basically randomly pick a port, and as the name suggests, these connections are short-lived, or these binds are short-lived. The client may pick a different port for each connection or each message. There is no telling which port to pick. You can obviously, if you're writing a low-level C code or low-level code, you can maybe pick the same port every time. But most high-level libraries won't offer that API to you. They'll just pick a random one. And so again, back to the code. This is what I was trying to tell just now. Once bound, the other sockets cannot use the same port. Address already in use is that error. Oh, and by the way, pro tip: if you're getting that error, this is a quick bash hack to kill all the processors that are listening to, say, port number 3000. I'll share this in show note later. All right, let's come to the next line, which is server.listen. Now, the number 5 there is basically the number of connections. Okay, hang on. Before we proceed to listen, any questions on bind so far? So far, so good. Anyone?
Hello.
Hello. Yeah.
Hey,
Hey,
how does SSL fit into this? Because the connection has to be secure some way, right?
Mm-hmm. All right. So SSL is part of the message or the data that is being exchanged. SSL in itself sits one level above socket communication. Even let's say you are sending a message, whether you're sending a secure message to a server or you're sending an insecure message to a server, the connection protocol remains the same. SSL operates on a different port for a variety of reasons. We're not going to go into that, but fundamentally the message you send will be encrypted, but you still have to send message. And so whatever we have seen so far is it all sits one level before or below SSL.
Okay.
Does that answer your question, or do you need me to?
Yeah. So basically, we tell this these sockets to communicate over HTTPS later.
So okay, all right. So socket is, so far we have talked about TCP level communication. HTTP is a couple of levels above TCP. So HTTP communication is based on TCP, and HTTP servers or HTTP entities that communicate using HTTP, in underlying protocol is TCP. So your secure socket layer, as it's called, SSL, or transport layer security, TLS, that sits sort of in the middle of those two.
Okay.
Is that, do you understand it, or do you want me to explain a little further?
No, it's fine. I'll look into that later.
Okay, let me explain a little bit again. So far, whatever we have seen is basically opening a socket connection and sending data to over that connection. We have not looked at what data is being sent. Now TLS comes into the picture, or TLS talks about what data is sent. It doesn't talk about how the data is sent. Does anyone else have this question? So if other people have the question, I can elaborate a little bit. Otherwise, we'll move on. All right. No answer. So okay. Sorry.
Yes, you can elaborate. I think.
All right. Let's elaborate a little bit before moving forward. So TLS, HTTP, they are what you call higher level protocols, or actually TLS is not a protocol. HTTP is a higher level protocol. HTTP sort of sits on top of TCP in the hierarchy. So what we have seen so far is how to send messages over network. What kind of code, what does the code that accepts messages and sends messages looks like? But TLS is, what TLS is saying is that here I am encrypting a message. When I send the message to the server or from the server to client, I'm encrypting it. And even if you read that message, you wouldn't actually figure out what is going on or what is the message really about. That doesn't change how we send the messages or how the messages are accepted on the server, or how the sockets communicate over the network. Is this any clearer? Like, if not, what we can do is we can come back to this and understand it a little bit later. What the figure you want to keep in your mind is that if you think of it as a pyramid, then TCP is sort of at the bottom, and then HTTP and TLS are above that. TLS is about the data, whereas what we are looking at right now is about the exchange.
Okay.
All right, so back to the second line of our, or the third part of our lifecycle listen. 5 is the number of connections your server can listen to. So how many connections should you listen to? Well, the thumb rule is that you can accept as many connections as you can handle. If you have too many clients and too few listens, then you typically have ERR, econ refuse, which means your socket is refusing to, connect. And if you have too many listens but too few clients, then obviously you're just wasting resources. Overall, again, this is there are thumb rules around this. Mostly, you come up with some kind of thumb rule about your system based on the experimentation you do. Most systems by default will not allow a single socket to accept more than 128 connections. That's sort of like the system max. There are configurations which will allow you to increase that number, but by default it's 128. Those are the max number of connections you can listen to or accept. However, how many connections we'll listen to is closely tied to the next stage in the life cycle, which is accept. Now, accept code looks something like this: connection, comma, we're ignoring whatever the rest of the things accept returns. Accept basically returns two things: the connection that currently is in picture, and then the address info of the connection. Address info is just purely technical details. We are not going to go into it right now. Maybe in the second talk, Aditya might have covered something about address info. It's not terribly important as connection. What do you do with a connection? You can read connections. There are different methods to read. You can read entire thing. You can read some bytes. You can read partial, etc. We'll go into details of each of these shortly. Accept, basically one accept call works on a single message, which means if you want to accept 10 requests or 10 connections, you need to call accept 10 times. If you write a simple code that code that we have seen one-liner, what that code will do is it will accept the one message and it will exit, which means you can only send one message and you're done. Fire and forget, single arrow. Which means if you want to do any kind of useful thing like a server, you need to run accept in a loop to be actually useful. And the code for that looks pretty straightforward. We already created the server. We created a socket. We bound it to some address and port, and then we started listening to say X amount of connections. After that, for that server to be actually useful, you need to run in a loop. This is what a loop looks like. Fairly straightforward. Server accepts the connection. You can read it. You can also write. This is the response part. So now, if you think in terms of request and response, connection.read is where you're reading the request. Then you do something about that request. If this were a Postgres server, I would maybe run the query and return the results. And then write is when you write back. Write is where the connection writes back to the client using that ephemeral port that we talked about earlier. And then close. Never forget to close. If you don't close, chances are either side would just be left hanging, and nobody likes hung up servers. The most important thing to understand here and in this life cycle is that accept is a blocking call, which means the moment you call accept, your code execution stops and it waits for your socket to give messages back to you or send or read the messages from the socket. It basically waits until there is a message. What that means is for us is that if you need to accept more than one message at a time, you need some kind of concurrency mechanism. Like threads or async or whatever, like your favorite concurrency mechanism is just fine. But if you do need to accept more than one, then you definitely need concurrency mechanism. If you look at the Ruby documentation, this is an example taken, paraphrased slightly, but taken straight from the Ruby docs. We are creating a a TCP server loop. Okay, this TCP server loop, by the way, is your syntactic sugar. Let's go back a little bit. Not here. This TCP server loop is the exact syntax sugar I was talking about. This, the moment you call this, it does all the things that we spoke about earlier. It creates a socket, it binds it to 4242, and by default, it binds it to localhost 127.0.0.1. You can also make it listen to the 0.0.0 interface. And then it creates this loop, the outer for loop, sorry, the outer do loop is for your single connection accept. Now here, what we are doing is we're creating a new thread every time there's a new connection, and we're basically handling them in parallel. Well, we are handling them concurrently. Parallel depends on many other things. We're not going to go into concurrency and parallelism differences right now. I think Aditya will cover some of that in his talk, actually most of that. But what this code is doing is that it is handling all those connections in parallel. Why does that happen? Because thread.new accepts a callable and immediately returns, which means the moment your thread is created, a new thread of execution is started, and then this loop returns, it will go and accept the new connection. And again, that new connection will get its own thread, and likewise. Now, if you write this code blindly without any kind of understanding or any kind of consideration of limits, you could easily overwhelm your server. So this is where design considerations come into picture. How many connections to open, how many threads to open, etc. All those configuration items that you might have seen in Postgres or Redis or various other servers, they're all about this particular block of code. How many connections to accept and how many threads of execution you want to allow. Whenever you're writing a server, you know what your server is going to do. If your server is like a simple stat server, you know you're doing very lightweight CPU calculations. Most of your compute is CPU bound, so you don't need to worry about performance so much. If you're doing disk writes like databases do, then you need to worry about those things. So all those design considerations sort of stem from this part. How many connections are you accepting, and then how are you acting upon those accepted connections? Any questions? So far, so good.
Yeah.
I had one question. So,
Sure.
so
please
Postgres,
continue.
for example, has a concept of connection pools. So,
Correct.
what does that mean?
All right. So, okay, good question. So, connection pooling. So, this is your bare minimum basic fundamental connection, socket connection. Now, this will work, and for a demo or for a simple socket connection, this works. However, for a complex system or a high performance or system with higher performance requirements like Postgres, this is not enough. There are a lot of corner cases Postgres needs to handle. What if the clients terminate requests in the middle? How to efficiently utilize system resources, etc. So considering all that in mind, connection pooling and other things are sort of a layer on top of this that add. You can consider connection pool as a robustness layer on top of this basic fundamental concurrent socket handling code. So what you would do is like connection pooling. It acts like on the pigeonholing principle, right? You will create a few connections, and then you will have sort of keep them available so that your clients can use it. The fundamental part of socket connection is that every connection is a TCP handshake. Every time you create a new connection, or your handshake is happening. So if you want to avoid all that, that's what connection pools do. They keep these connections open and then allow you to sort of use them so that you can efficiently write, and you don't end up wasting time in opening and closing connection every time. You can think of that as a 100 open phone line. There are 1,000 people in a room who want to talk to 1,000 people in another room, and there are 100 open phone lines. So without connection pooling, you can consider like there are 10 phone instruments. You go and dial and talk. whereas connection pooling is like you dial and keep the line open, and then you manage some sort of queuing on the one side, where people just come and talk on an open line and then they go back. So connection pooling and connection pooling is sort of like a efficiency mechanism built on top of TCP connections. Does that answer the question?
Yes, that makes sense. Yeah,
Cool.
thank you.
Hey, Aditya, Prathamesh, or Nishan, do you guys want to elaborate or expand on that? Or anybody, like? If not, we can move ahead.
Yeah, I have a question regarding.
Sure. Go ahead, Anubhav.
Yeah. So in the previous slides we had socket.listen bracket 5, right?
Which one? Which one?
In dot listen.
Oh, okay. Socket.listen. Right. Yes.
Yeah.
Yeah.
So how does
Right.
this loop thing like whenever the loop goes on and we start a thread, then how does that connection thing relate to this? Like,
Okay. Yeah. Welcome to the wonderful world of sane defaults. So TCP server loop has a whole bunch of options which allow us to cover each part of the life cycle. For example, 4242 allows us to specify which port. You can also say which listening interface. Similarly, you can say list how many connections to. By default, it I think in Ruby by default there is no limit, so it'll default to the sock max, which is 128. In some libraries or in some standard libs, 5 is the default. In some cases, 10 is the default. So the defaults vary, but by default, it will pick something. Convention over configuration. Socket.tcp server loop has a number. It will pick that number and start listening to those many connections. So what this does is, the moment you call socket TCP server loop, it creates the socket, binds it to the port and the interface, starts listening to the default number of connections, and then the loop basically runs on accept. Make sense?
okay, so connections are made and loop only runs when there is a accept, right?
Yes. So what this is doing is it is running the accept method in a loop. Internally, TCP server loop just calls loop do. Remember our earlier loop method?
Yeah.
This one. So the TCP server loop does something like this internally. Actually, it does exactly this in a slightly different way. So before calling the loop, it's going to create the socket and bind and listen.
Okay.
And then it's going to call the loop.
Swanand, I have a question.
Sure.
So in this loop slide that you are showing, so this particular server.accept read write close. So this is a part of a single thread implementation.
This is single thread. You're right.
So basically, whenever you are spawning a TCP server on a particular port, so there will be, I guess, like 128 threads or 5 threads, depending on like how much you have configured. So 5 threads will be running in this particular loop format.
In this loop, only one thread is running. We are not creating any thread right now in this particular loop. What is on the screen right now? This is a single threaded loop. We're not creating any. So what this means is this loop runs. It calls accept once. That's going to wait for someone else to send a message. That message comes in. It'll handle that message and then go back to loop. And again, it will wait on the accept blocking call. So let's say there were 10 clients wanting to send a message to this particular server. They will basically just have to, if one of them is sort of in the middle of talking, the others would get connection refused. Because we are not doing any kind of concurrency here. At a moment, the server can only accept only one message, which means the others cannot actually connect. So they're going to either time out or they'll get connection refused.
Okay. And whenever you scan a server, so all these ports, all these threads get created beforehand, or is it something that is done on demand?
I couldn't understand. Sorry, your voice is not very clear.
I mean, like in Rails, you have a connection pool where you specify like, you want to have 5 connections, but those 5 connections are not created at the start of the server. They basically get called whenever somebody asks for a query, asks for some results and send in a query. So does this?
Okay. You're okay. So you're conflating between client connections and server connections. This is server connection. The connection pool that you talked about in this, that is the client connection to talk to the database server.
Okay.
So that is what Girish asked some time ago. That's what the connection pool does. This we are talking about is server, which means it could be the Rails server itself wanting to read data from the HTTP request, or this could be like the Redis server or Postgres server or any other server.
Okay.
Is that clear? Okay. Any other questions? I think it's actually fairly important to understand this before we move on.
I like to add a few things.
Sure. Who is this, by the way?
Oh, I'm Swanand.
Sorry to disturb, but whenever you're asking any question or adding a comment, just say your name, because otherwise we are not sure who is speaking. So just introduce yourself and then start speaking.
Hi. So I'd like to add one thing that people probably were getting confused about is like the listen syscall basically gets an argument in one of the code we had written that it should listen to 5 connections. It just indicates to the server, I think, that 5 clients can be basically in the queue. So they'll be just waiting for the server to accept a connection. And if there are more than 5 clients, the 6th client would just get a connection refused error, and the rest of the 5 clients will just keep on waiting until the timeout occurs, if I'm not wrong.
Correct. Yep, that's exactly right. So that's called, in fact, the number 5 is called the waiting queue in terms of the system call arguments. How many like the network layer will accept those many connections and keep them sort of waiting until the socket or the socket responds to those messages. This is different from your connection pooling. This is not connection pool. Even though 5 waiting in a queue sounds like a pool, this is not your connection pool. This is just a simple queue, like going into a bank or something. There are 5 counters. That's your 5. Or you could say, social distancing. Only 5 people can wait in the queue, something like that. How many people or how many messages can wait at a time? Any other question? Any addition? Anyone else? All right, let's move on a little bit. We have few more things to cover. So yeah, in this particular slide, the connection.read is your message. If you were sending an HTTP message, for example, this would read something like post to HTTP/1 with headers and then body, etc. Or if you're like Redis, then you will have something like set nx, some value, these kind of things. So that's your message, and then connection.write in this, that's your response. So request and response. So this in fact is a fully functional socket server. This is actually if you write this code and run it, it's going to work. You can send messages to it and it'll respond back with hello world every time. No matter what you send, it's just going to respond with hello world, because that's what the code says. A fully functional socket server, and yet it has a major flaw. If we run that server, let's say in terminal 1, Ruby socket server, and it's running on some port 404242, and in terminal 2 we did this tail -f foo.log, and then nc. So nc is a terminal utility called netcat. What it does is it echoes or sends output. Actually, this code is not exactly right. I forgot to add echo before it. Anything you pass on to the std in of netcat will pass it on to the server listening on this interface, localhost 4240. So let's say, so in this case, for example, the output of tail is piped to nc, and then nc will simply send that message over the socket to the server listening on 4242 on localhost, which is our server in this case. Now what is going to happen is, this server will wait forever. It's because read is greedy. Connection.read tries to read everything that is sent to that particular socket, and it will wait for an EOF signal or an event. And tail never sends EOF. Tail, it doesn't end, right? Even if the file sort of ends, tail minus F, for example, it never sends an EOF. Even if your file is 10 lines long or 2 lines long and you do tail minus F, it will basically print those 2 lines and it will simply wait for the file to change or add new files, which means the server basically just keep on waiting. And that's not good, right? What is happening is our server behavior is now sort of getting controlled by the client, which is never a good thing. So what now? How do we fix this? Any hint? Anyone? That was an attempt of a joke. Enter the buffering. This is where the concept of buffering comes in. When we read data or write data, we may choose to read partial data, or we may choose to read all the data. Similarly, when we write, we may choose to write partial data, or we may choose to write all the data together. And writing it in partial is called buffering. So for example, connection.read is basically you must read all data. If you send a number of bytes, read takes an argument number of bytes, then what it'll do is it'll wait until the client has sent 100 bytes. Again, which means that if you say connection.read 100 bytes and the client only sends 50 bytes, you will just keep waiting until an EOF event occurs. EOF event typically occurs when the client either closes the connection or an actual end of file happens. So, and then read partial is the answer to that. Read partial, reads it and returns immediately. So if you had to memify, connection.read and connection.read X number of bytes, that's something we don't want. What we want to do is read partial. So the thumb rules around reading and writing are like this. When you're writing, write in one go, and then rely on the lower level handling of buffering. Your network and lower level syscalls, they do some internal buffering. Kernels and operating systems know how to handle the network resources the best. Definitely better than higher level code. So for writing, we typically rely on that. However, reading is different. When we are reading, we must actually buffer. 16 KB is sort of the standard buffer length for many Ruby libraries like Unicorn, Puma, or I think Nginx by default. And I think a couple of other, they use 16 KB as like the default read buffer. Redis RB for some reason uses 1 KB. I've not really found any reason as to why they do it. Maybe Antides has some sort of documentation somewhere. So how do we use read partial? Well, read partial, what read partial does is you keep reading and it basically throws an EOF when there's nothing more to read. And then at that point you accumulate and handle data. And so this is like a weak implementation of how read partial would sort of work. The main meat of the whole thing is in sort of accumulate and handle in this code. So that's it. So this combined with our multi-threaded server that we saw a little bit before is how this is like your bare minimum socket. Everything on top of this is now like network and other design considerations. But whatever this code we've seen so far is a fully functional TCP server, which can respond to any request that you send to. That's it. That's all I have so far. I have some more code to show. Maybe I'll take a little break, and then after that I can maybe at the end of the meetup I can show some code. But that's all I have so far.
All right.
I'm happy to answer questions.
I see one clap from Swanand.
Okay, thank you.
Is there any question? Ashwin, you were saying something about syscall explanation. what exactly you're saying.
I think Ashwin is on mute.
Okay, it's already sorted. That's great.
Okay, some people have sent notes in the chat. Pretty cool. Yeah, that's helpful. Cool. Yeah, the SSL bit, definitely I can see how that could be a little confusing. Again, the pyramid diagram is helpful. Like we have to understand where socket communication is happening and where TLS is happening. That is the sort of distinction which will help you understand why and how TLS is different from what we saw today. Cool.
Cool. So we'll give Swanand a bit of break now. I think he needs some water. All right. So we'll give Swanand a bit of break. Should we move on to the next talk immediately? Aditya, are you ready?
Yeah, I can start.
All right. So we can start with the next talk. Just would like to mention again that whenever you're asking any question, just first say your name so that everyone can figure out who you are, because we have 36 people, so it's a bit hard to understand who is speaking. So we'll start with the next talk. Almost everybody must be knowing Aditya. So we can start with his talk about, again, sockets. So let's see. Can we have a 10-minute break? Sagar is asking. I'm fine with it, but 10 minutes break.
I think let's take a 5-minute break. I think 5 minutes might be.
5-minute break and then come back.
Great.
Okay, till then I'll test screen sharing and all that stuff.
Yeah, all right. So we'll be back at 18:10. All right, Sagar has joined again, so I think we can start now. He asked for the break. Can everybody enable their videos? We can take a quick photo before we start the talk. Let me see.
Turn those backlights off.
I think it is everybody is enabling their photo after 1 or 2 minutes. So we are still waiting for the people at the bottom, backbenchers.
Backbenchers.
Hey, we have Pradipto here. Hello. Long time.
Oh, hey. We have
Hi,
celebrities.
I came to learn. I don't know if I was a celebrity or not. Swanand told me that there is a session happening. I didn't. Aditya and I was speaking to you earlier. I wish I knew earlier. I would have been better prepared.
We are still waiting for some people to start their photo. Ratnadeep, Vipul, Sharang, Tejas, Tanmay, Sagar, Udipa, Muni. Or you don't want to start your video? Okay. All right. All right. I think we can start. Aditya. We can.
Okay, let me share my screen. Cool. Is the screen visible to everyone?
Yes.
Am I audible firstly? People at the back?
Yeah.
Okay. And text is also readable, right?
It is. Yeah.
Cool. So let's start. So I'm going to sort of build up on what Swanand covered somewhat, and a couple of things. What the concepts I'm going to talk about are not limited just to Ruby. They apply equally to languages like Python and Java, and yeah, just leave it to these two for a while. Also, what I'm covering applies to both the server side and the client side, but for the purpose of understanding, just think of it as being on the client side for now, and then later on you can, once you've grasped the whole thing, you can think about how it applies to the server side also. So before we start, I just want to do a quick sort of catch up on what threads are and what a thread looks like for a Ruby programmer. So a thread is a construct using which you do concurrency, and in Ruby, a thread maps one-on-one to a operating system thread. So every time you do thread.new, there is a new operating system thread that is created underneath. For every thread, typically the operating system will create a stack in the kernel. It's usually 8 KB, but it can be configured. And this is locked because it's in kernel space. So this 8 KB per thread is non-swappable memory, because fundamentally you cannot swap out the memory of the kernel itself, because if you swap out kernel memory, there's no one then left to bring it back. It's like Sheikh Chilli cutting the branch is sitting on, right? You can't just cut your own branch. So and a thread also has its own user space stack. So that is where all the variables that we create as programmers live in the thread. And especially in Ruby, which has abstractions on top of the threads, some memory is assigned for the Ruby object, which encapsulates this OS level thread as well. Now, any thread has, it can be in one of the following states. There are actually more states, but I've just noted the ones which are sort of relevant for this talk. So the states are running, sleep interruptible, sleep uninterruptible, and stopped. So a running thread is a thread that is active right now, which means that it is utilizing the CPU. There are instructions, CPU instructions running in the context of that thread. Sleep uninterruptible means that it is sleeping. Actually, this is the other way around. Sleep uninterruptible means that it is sleeping on a IO call. So for example, if you're doing a socket.read or a write to a socket. So these are IO calls, and like Swanand mentioned, these are blocking calls. So basically what blocking means is that the state of the thread is changed to sleep uninterruptible whenever you're doing these IO input or output calls. There is sleep interruptible, which are threads waiting for some external event, like it can be a sleep call or the sleep method that you invoke just puts the thread to sleep and it waits for a timer event. So there are other events that a thread can wait on, and threads in that state are in the sleep interruptible state. Runnable is a state which is like an intermediate state where let's say the event has occurred or the data is ready for consumption, but the thread is not yet running. It is ready to be made running anytime, but it is not running at that particular moment. So threads in that state are runnable. So for example, if you're doing a socket.read and the data becomes available, then the point at which the data becomes available, the thread will move into a runnable state. And then the operating system will decide, okay, let's start running this thread. And like I mentioned before, a read call puts the thread in a sleep uninterruptible state. Now, what's peculiar in Ruby is everyone has heard of the global interpreter lock or the GIL. What basically it does is, for backward compatibility reasons, the Ruby interpreter allows only one thread to be in the running state. Okay, which means only one thread has its instructions actively being executed on the CPU. You can have any number of threads as long as the other threads are in one of the other states. So you can have any number of threads on which you're doing a socket.read, in which case all those threads would be in a sleep uninterruptible state, or if the data is available, they would be in a runnable state. But only one thread, like I mentioned, can be in the actual running state. Okay. What I'll do is I'll pause in between these small logical sections and see if there are questions. So any questions so far? None so far. So I'm guessing.
Oh. So what's on the comments, right? Sleep uninterruptible and sleep interruptible. Those two are swapped, right?
Yeah. So actually, let me just. Shall we go ahead? Okay. So with that knowledge and whatever Swanand has covered before, let's take a look at some code which is creating client-side TCP sockets. So I have a server running in the backend. That's a simple echo server. Whatever it gets, it just writes back on the socket. So if you write hello, you're going to get back hello when you read. So what I'm doing over here is I am basically running a loop, and in every iteration of the loop, I'm creating a socket pointing to the local host address and port 8888, and the echo server is running on port 8888. I am writing the string hello, so I'm sending this string over the socket to the server. Then I am starting a new thread. Okay, so thread.new creates a new thread in Ruby. Okay, this thread, if you see, this is the last sort of block in the loop. So the return value of thread.new is what is going to be returned from this block, and map will just be then this list of threads that have been created. Inside this thread, on the same socket, I am doing a receive call. So I'm just, so Swanand showed a couple of higher level calls to read from a socket. This receive maps directly to the system call, the POSIX system call. So I'm using that interface. I'm reading at the most 64 bytes, which is more than enough to read our hello string, right? I am printing the data, and then I'm doing a sleep one just to simulate a long read. So it's actually two reads with one of, it's two blocking calls. One of the blocking call is the receive and one is the sleep. But just so that everything doesn't go super fast, I am inserting an artificial sleep of 1 second over here. Okay, and that's all that happens in the thread. And over here, so the map method is just going to accumulate all the threads into a list, and that is this threads variable. And I am looping over each one of them and calling the join method. So the join method on a thread waits for that thread to finish. And what we are doing is, in a loop, we are just waiting for every thread to finish. So this program will wait till all the threads have finished. Any questions on what this functionality is? Okay.
Aditya, I had one doubt. Like,
who is this?
This Girish. Sorry. Yeah. So line number 27, TCP socket.new. You are creating multiple sockets that are listening on the same port here.
Yes.
So this won't give that error port already in use?
No. So those are, so on the server side, this is the port that the server is listening on. Okay, so like Swanand said, on the server side, you basically have a port address, and the server has implemented a listen call. And once a connection is available, you have to call accept on it, and that will give you the file descriptor on the server side.
Right.
So you can have only one. You can have one port on the server side accepting multiple connections. Now, what this TCP socket.new does is, it will automatically find the available port on the client side. Like, both sides need a port assigned. Here, to TCP socket.new, you can explicitly say, I want this particular port, but the client side ports are throwaway ports. Usually you don't say that I want this specific port on the client side, because most of the time you don't care what port is assigned.
Right. Yeah.
So
I forgot we were looking at client code.
Yeah. Right. So in this scenario, this is all client side.
Yeah. Okay.
So any more questions? Okay. So let's run this. So I'm just, when I start this, when I run this program, it's just going to call with the argument of the number of threads that I want, or the number of sockets. And I'm just running it. So if you see over here, I basically ran it with time to just get some basic stats. So the memory used in this case for about 2,500 socket connections was about 60 MB. Okay, and if you can see, the system memory is, or the system time spent is 1.03 seconds. User time was 0.52 seconds. Real doesn't really matter. Okay, but the problem with this is, now can I do 25,000? Right. So I won't run it right now. The answer is you cannot, especially on, so on the Mac, for example, the number of threads is limited to 2048 per process. I mean, you can do a lot of tweaks to change that limit. But basically, if you spawn a large number of threads, like I said, for every thread, 8 KB of memory is locked in the kernel, and this is memory that is locked in the RAM. So 2,500 multiplied by 8 KB, that much memory is locked. You can't do anything with it. So usually it's frowned upon to spawn a very large number of threads, because they kind of eat system resources. So here is a example, like I'd done some tweaks and ran with a very large number of threads. So what happened, if you see over here, was it reached a stage where it could not create more threads. If you're on Linux, this limit is usually not there, but the amount of resources that you will consume is still going to be the same. So this program kept on running. It at its peak went to 106 megabytes of RAM, and there's nothing else in the program. If you see, it's just creating sockets and creating threads to connect, and then it just errored out because the OS wouldn't let it create more threads. Okay, as you try to increase this volume of concurrence, if you go to 10,000, 50,000 simultaneous units of concurrency, this resource consumption of every thread starts getting in the way. Okay, so usually for very high level of concurrency, a pure thread-based solution like this is not going to work. So what can we do now? Hang on, we have a question. Does thread limit also apply when we work with servers like Puma? Yes, it applies to any process. You can tweak the OS parameters and make it support more threads or not, or raise the limits, but the limits are usually there to protect from heavy resource consumption. Even if you increase the limits, the resource consumption is still going to happen.
Threads, what Aditya is talking about right now is independent of whether you're creating them on client or server. It's with any OS or any system.
Yeah. Okay, so how can we solve this problem? Now, let's see if there is a way where you can actually read from multiple sockets using a single thread. Okay, now let's assume can everyone see this window tab, browser tab?
Yes.
Okay.
Yes.
So let's assume that you have a function or method called as shortlist. Okay. What this method is going to do is it is going to take an array of sockets. So these are the candidates from which we want to read. Okay. And what it returns is a subset of the input for which data is available to be read. Okay. This method shortlist is going to wait till there is data available for any of the sockets. So for example, you call this method with say 10 sockets. Out of those, 2 sockets get data available for reading from the server. Again, think only client side right now for it to be easier to understand. You have you're waiting for input from 10 sockets, which are going to get data from the server. And out of those 10, the server has sent a response on say 2 sockets out of 10. Now the shortlist method is going to stop blocking and return, and it is going to return the subset of the input array for which data is available, which means that if you do a read on any of these sockets, it is guaranteed not to block because data is already there. You're just fetching the data from the internal buffers. So it's guaranteed not to block the thread. Okay, this is a very fundamental part of the whole talk. So it's important that you understand this. If you have not understood this, I'll stop for a minute to take questions.
Maybe you can repeat it one more time.
Okay. So let's assume there is a method called shortlist. It takes an array of sockets. These are the sockets in the array are the ones for which you want to do a read call. So instead of spawning 10 different threads and in every thread calling socket.receive, you are just sending all those sockets in an array to this method shortlist. Now the shortlist method is going to block. till what point is it going to block? It will block until there is data available for reading on any of the sockets. Now the data can come one by one, right? In which case, maybe first time the shortlist method will just return one socket because data is available only for one socket. But let's say data is available for 5 out of the 10 sockets at the same time. In that case, the shortlist function or method will return an array with 5 sockets. Okay, so the way you interpret the return value of this shortlist method is if you do a read call on any of the sockets in the return array, then that read call is guaranteed to not block because there is data available for it in the memory buffers already.
I have a question.
Yeah.
Yeah. So how does we get a confirmation that data is available to be read?
So if the data is not available to be read, then that socket won't be included in the return value. So the return is an array. There are multiple sockets in that array. So only those sockets for which data is available is returned in the array.
Okay. So which the sockets which have data in them, these are the ones that are included in the array, right?
In the return array.
Okay. Yeah.
So just to do a Ruby-like syntax, maybe I'll say
dot select
readable equal to shortlist blah blah blah, and this readable is array. Okay. So you pass it a list of sockets and it will block. It will block till there is data available on any one of them or more than one of them. And it is going to return a list of sockets from this, which is a subset of this input array, into readable. Okay. Clear?
Yeah. Thank you.
Okay. Now, what do you do with this return, right? So step 2 is, so let's say that this return is called ready list. That is the name of the variable in which you are taking the return. So let's say this is a ready list equal to. Okay. Now for each socket in the ready list, you are going to read. Okay. There is a variant of the receive method called as receive non-block, which is a non-blocking receive. Now, since every socket in this ready list was returned by this shortlisting method, it is guaranteed that receive non-block will also return some data because there is data available. You don't need to wait for it. So you take this data, okay, and for now, let's assume that this socket variable is a subclass of the actual socket, the actual TCP socket class, and it has a callback block embedded in it, or a callable block embedded in it. What that callable block is basically once you get the data for that socket, you want to call this callback block and pass the data to it. So this is very similar to your Node.js style implementation where you're passing a callback and saying that once data is available to this for this socket, call this callback function or method or block and pass me that data. Okay, so we are assuming that there is this callback attribute embedded inside the socket which you can call and pass the data. So what we are doing is on the ready list, we are just iterating for each socket. We are fetching the data and we are executing the callback for that particular socket with that data. Okay, clear? Second step. Any questions? No questions?
No, one question.
Yeah.
About the shortlist method. So the shortlist method is something provided by the API, or it is
Yes, yes, it is provided by the API. We'll soon see what it is.
Okay.
Okay. Now to actually complete our whole thing, what we want is we need to add another step. So I'll add it over here as step 0. Okay. Now what we are going to do is, how do we get this list of sockets, right? So let's say we have a queue, and in that queue, people are going to put read requests. Now every read request contains the actual socket and it contains the callback. So you can think of it as each one of these is an instance of this ASOC class, because it is a socket and it has the callback embedded in it as a member. So each one of these blocks over here, you can assume that they are an instance of the ASOC class. So if somebody wants to read from this particular socket, they will just put that socket in this queue. Okay, and then we have a loop that is going to do this. First, it is going to fetch all the candidates for reading from this queue. Second, it is going to call the shortlist method. I'll just rename it to candidates here. Okay, so this is step 0. Step 1 is this, and it is going to give a response, which is the ready list. Sticking to Ruby conventions. Okay, and then we are going to loop over all of them and do a callback. Okay, and this we are going to do in a loop. So this is going to be our read loop, which is going to be continuously running, or at least till there is some terminating condition, which comes externally. Unless someone asks us to stop the loop explicitly, we will have a method which is going to just loop over this. Okay. Conceptually, are these 3 steps and the loop clear?
Yeah.
Okay. This method shortlist is called actually select. Okay, this is a method provided right up to the operating system, and it is available in the Ruby standard library also. Of course, the select method takes a read candidate list, a write candidate list, and some timeout conditions as well. I have simplified it just for the read candidates list. So I'm not covering writes over here because they just complicate the talk and the explanation, but conceptually it's the same. Okay. Shall I move ahead?
Yeah.
Okay. Now let's look at this. So just like we had a blocking implementation, this is a implementation based on this selector and this select that we have written. If you see, you'll probably be able to see a correspondence between these two, right? So step 0, so in 47 and 48, we are getting all the candidates from the queue. Here, if there are no candidates, this is just some housekeeping. If there's no request for reading, I'm just inducing an artificial sleep of 1 because I don't want to do a tight spin. Like I just don't want to loop very fast. So I'm sleeping for 1 and then redoing the whole iteration. If the ready list, if the readers is not empty, then I call io.select and pass the readers, very similar to this, right? This returns me a ready list, and for each item in this ready list, I call read and callback. So the 2 lines inside this block in step number 2 I have actually implemented in the class ASOC itself. So on the socket, I have implemented a method read and callback, which does the equivalent of these two. I'll just show it quickly. So this is the read and callback method, line number 17 to 20, which basically do these two steps. Okay, so in terms of process, this is exactly what is happening. Why I put it in this is just for convenience of the API to access. Okay. Now the rest of this code is actually plumbing, where I'm this run method is a method on a selector class, and I have convenience methods on it which create a new connection. This new connection is, I am initializing this sSocket class, which maps to this ASOC class that we have over here. Now, what I've done is each one of these objects of the ASOC class know which queue to put themselves on. So I've sort of tightly bound the ASOC class with the queue that they should be putting themselves on. So which is why they're created in this new connection. I'm creating it and I'm binding the reactor called self. Okay, and the async method on the socket does not actually do any read. It just stores the callback, the max bytes, and it schedules itself for reading on the reactor. So what this method is going to do, this async read, is just dump this socket in the queue over here. Okay, and the run method is then going to pick up this socket and then call select on it and the rest of the process. Okay. So the rest of the code is sort of just stitching things together, but the core logic is this loop that I have demonstrated over here, step 0, 1, and 2. Okay, and again, this selector method, this wait group and all this is just a way of waiting till all the work is done, basically. So wait group is like a countdown semaphore. Don't worry about it if you don't know about it already. If you have done any Go programming, it's exactly the same as the wait group class in Go. Basically what you do is you initialize it with an integer, and then every thread calls done on it, and there is one thread which is waiting, and the wait will return after the count has reduced to 0. So every time you call done, it reduces the count by 1 in the work group, and once it becomes 0, this will return and it stops the reactor. So all this decoration around the whole thing is just to make it exit cleanly. That's it. But you don't have to worry about it. Just assume that it's some way of waiting for all the work to be done. That's it. Now, but what I'm doing in the selector method, this is the core of it. I'm creating count number of sockets. For each one of them, I'm putting hello. So this is very similar to the blocking RB, right? Over here, I was doing socket.receive in a thread. Instead of doing it in a thread, this is a single thread now. I'm calling putes on it, and I'm calling async read. Okay, this async read, like we saw, is going to call this method, which is going to put the socket in the queue, which will then be consumed by the loop. And yeah, once data is available, it comes in the response. I am putting that response here, and I'm signaling that we are done. Okay, so conceptually it's very similar, except that we are not creating a new thread. Right? There is one thread somewhere which is catering to all the sockets that need reading in a single thread using the select call. Now, if I run this, so firstly, one thing you can see is obviously the load on the system was much lower. system resources used 0.21 system time, user time 0.17 instead of 0.52. What is worth noting is also that this consumed 15 MB instead of the 60 MB. And interestingly, if I just write a program which does not listen on any socket, just the base Ruby VM consumes 11 MB, right? So reading from 2500 sockets is adding 4 MB of overhead. Now, let's see if I can go to 3000. The reason I'm not going beyond 3000 is the file descriptor limit. Let me do 2900. Yeah, so I increased it by about 400 and it increased what, 1.6 MB of usage. So overall, it's much lighter on the system. Again, the load on the system 0.26 and 0.2. So this is a much more efficient way of doing concurrent socket programming in Ruby. Now, this algorithm or this pattern of doing things is typically called the reactor pattern. And this is exactly what Node.js does behind the scenes. Node.js has a thread that at its core implements this loop. And it has a queue where people queue things for reading and writing. Of course, it's more complex because there is reading, writing, there is timers, there are all sorts of events. But fundamentally, for all of those types of requests, this is the loop that is executed. Okay, and to sort of show a demonstration, this is the corresponding core. If it's not visible, let me, yeah. This is the corresponding core method from the event machine implementation. Right. So if you see again, this caters to read and write both. So you'll see reader and writer both, and you will probably see a single select call. Yeah, single select call for reader and writer. But this is a toy implementation for the purpose of this talk. But the core logic you can see is similar. Right? It is dequeuing, it is calling select, it is calling a method which is going to call the callback. And over here they have a array and not a queue. So instead of pop, they're just selecting from the array and then deciding which ones to delete. Whereas here what I've done is I've popped everything from the array, and the ones which have not been processed, I'm requeuing. So same thing but different implementation. They're deciding what to remove, I'm deciding what to put back. Okay, so you can explore this implementation of event machine. This is the place where you can go out. It starts getting complex pretty fast because, like I said, there is timers, there is readers, there's writers, all sorts of things. And one thing that event machine does for you is it also implements a thread pool on which you can defer certain blocking tasks. So not everything, for example, if you're reading from a database, you don't have event machine implementations for handling the connections in that database library, or not all of them do. So in that case, you will have to basically you do a blocking read, but then it gives you a ready-made thread pool on which you can offload that so that you don't block the main event loop. Now, one thing that you have to be very careful, and also true when you're doing event machine, right? Let's say I do sleep 1 over here. Okay, so in the response of the async read, I'm adding a sleep 1. What do you think will happen? Anyone? So sleep one is going to block this thread, right? But which thread is it going to be blocking? So it is going to block the thread that calls this block. So this block that you have, this block is doing a sleep. So the thread that is calling this block is going to sleep for 1 second. Now, what is the thread that is calling this block? This block is being called from here, read and callback, right? This is the method that is being called. And this read and callback is being called from this loop. Okay, so here. So if you put a sleep in your callbacks, it is going to block all the entire event loop. So all the sockets which are waiting for data, the processing of all the sockets is going to be blocked. So I'll just demonstrate that. This is something you have to be very careful when you're using event machine. If this is one thing you take care of, then you're absolutely fine using event machine. So I have no idea what this is going to do now. Like forget 2900, let me run with 10. Boom. Did you see? So every single thread or every single callback blocked the entire reactor thread for 1 second. So if you see over here, it took approximately 10 point something seconds. So that is one difference between event machine and say Node.js. In Node.js, it is impossible to do a sleep like this. Even a sleep will have to be done with a callback. So the main difference between event machine and Node.js is that the entire Node.js library, there is no way of doing any blocking call. So there is no way you can block the entire reactor thread. But if you're using event machine, you can do that. So although event machine allows you to scale to like even 1 million concurrent processing units or concurrent threadlets, so to say, at a time, if you even do any blocking read in any one of them, the entire reactor loop is going to block. So once you are careful about this, then you can actually get a lot of high performance network IO using just event machine. And like I said, if you want, and that is why event machine provides that thread pool. So this sleep one would usually be done in a deferred manner on some other thread pool with a callback. Okay, so that is why event machine provides this separate thread pool on which you can do the blocking read or write calls. So yeah, that was pretty much all I wanted to cover. It's kind of difficult to grasp all at once because quite a few core concepts and probably difficult concepts were covered, but hopefully this gives you a starting point to explore. I'll share this code on GitHub, send it on the meetup group so that you can dig more into it, play around. You can also look at how wait group has been implemented using the Ruby synchronization mechanisms, because wait group is not a standard thing in Ruby. I just used condition variables and mutexes to implement it. So yeah, open to questions.
The quick addition, Unicorn's source code is pretty good in this. They do a lot of IO and read groups and blocking.
Yeah.
If you want to read like so like a follow-up read, Unicorn's code is pretty nice.
So one thing is, so far I've been talking from the client point of view, but now you can expand your assumptions and also see that this will also apply on the server side, because reading from a network socket is basically what the first step that a server does, right? So even if you are implementing on the server side, the first thing that if you even look at Swanand's slides, the first thing that you did was read from a socket, so that then you could write to it. So this read mechanism of doing non-blocking read will apply even on the server side. And that is basically what, if you use event machine with a server like Thin, or event machine has its own HTTP server implementation, HTTP client implementation. So event machine provides one more layer of these connection libraries on top of the core of event machine. And that is what is used by things like Thin and probably Unicorn, as Swanand is saying. I have not seen Unicorn, but Thin definitely can use event machine if you ask it to. So it won't spawn one thread per request. But then if you do blocking read or write in your request handlers, then you are going to block the whole reactor.
I think there is also a WebSocket related gem that is using event machine.
Are there any Python people here in the meetup today? Anyone who's written a little bit of Python? Python has a nice server called UWSGI. I think that's what they call UWSGI. It also has some really good socket semantics, thread semantics from a server context.
Yeah. So the Python equivalent is Tornado, right? Or Twisted, or one of those two. So the Python equivalent of event machine is either Twisted or Tornado. I'm not sure which came first or what builds on top of what.
Okay, somebody's asking about socketry or async gem.
So what socketry does is, I'll give you an analogy. So when Node.js came, you had all this callback way of writing code, right? You made a call and you passed a callback. But then now, if you see modern Node.js code, you have this async await mechanism. So the socketry, async, and there's another one which is very similar. They provide you that kind of API on top of event machine. The socketry, I'm not sure whether it provides it on top of event machine, but there is another reactor implementation. I think socketry works on top of that. I'm not exactly certain.
I think the async gem itself is a reactor implementation.
Okay. Yeah. So Falcon and async, they are a parallel implementation. On top of event machine, there is a async await kind of abstraction, so that you can write sequential code instead of doing callbacks. Exactly the same what happened to Node.js. Actually, we can just, I forgot what to even Google for. EM. No, it's giving me JavaScript. I don't remember. I can look up and tell you. But there is a similar to the socketry universe. There is a parallel abstraction on top of event machine also.
There's one server, I think it's Goliath. I may be wrong here, but I think it's based on reactor pattern. Maybe.
Yeah. So there are quite a few that are based on reactor patterns now. So for example, like the very core one, if you want to take a look at. So event machine project itself provides you with a HTTP server, which is based on the reactor pattern. And it's a very lightweight server, which is, you can use it for very basic stuff, but event machine plus Thin is actually a very good combination if you want to do async using event machine. There is Falcon, there is Goliath, quite a few of them.
The WebSocket gem that I mentioned, that was also using thin and event machine.
Which one?
There is a gem, but I think it is outdated now because of
Okay.
But there was a gem for Rails 4. I think it was called WebSocket Rails.
Okay.
Also using thin and event machine.
Yeah, so you'll see this pattern implemented multiple times, but like I said, as long as you understand this mechanism, everything is going to be a variant of that. Any more questions?
Hey, so I've been meaning to ask, is there any fundamental difference in select and poll? Like the way I understood, they're quite similar, only minor differences.
So select is the system interface is called select. ePoll and KQ are implementations of that interface on different operating systems. Unless there is a interface called poll also, but I've never used it.
Because I'm used to using select.
Yeah,
like
I mean, as a
research for
programmer,
this talk,
as a programmer, I've only used select. ePoll is, there is a poll.
Yeah, like during the research of this talk, like poll kept showing up, so I was not sure because when I did back in the day, like select was the thing.
Okay. Okay, it seems that poll handles more than just network events, whereas select is specifically only on file descriptors and sockets.
By the way, for others, the further reading, select, like the design license and how to use select would be the perfect further reading.
Yeah, I saw a few recommendations for books. I was going to recommend one, although it's in sockets, networking API. Yeah, so there's this book called the Unix Network Programming by Richard Stevens, I think. There's no actor called Richard Stevens, right? Yeah, then probably this fellow. So it's in C, but it covers all the concepts that both Swanand and I talked about today. Not the reactor pattern, but it covers select and all of that.
Yeah, I mentioned that book only in the chat there.
Okay.
I started reading that, so.
Yeah, so that covers everything right from details of the configuration options for sockets, non-TCP sockets, like everything. So that I would highly recommend that book.
One fun way to learn this, which I followed when I was learning this many years ago, with the mentor I had, he paired us in buddies, and then one person would write the server and the other person would write the client and try to break the server, and then you take turns sending whatever, either send weird data, send too much data, that kind of thing.
There's a question from Sagar. Can you talk about real life problems? Oh, I have many. Achha, like prod server config and failed when number of connections crossed. I mean, that's the whole reason why Rails got a bad rep, right? Because it could not deal with a large number of concurrent requests at the same time. And then people started coming up with alternatives like Thin and like Falcon and all of that. So every time people say that Rails does not scale, basically they mean that Rails does not scale in the standard one thread per request model, and that they haven't tried it. the other model. But frankly, I have not encountered a Rails server being loaded so much that it is refusing connections, especially because nowadays you have things like auto scaling and all of that. So at a particular threshold levels, you can just bring up new servers, and the load balancer, AWS or any cloud load balancer handles that. But then the price or the cost you pay is more number of instances and higher memory and CPU utilization per instance as well. So yeah, that's my answer. If anyone has actually run into a problems where the server started refusing connections.
One thing that we had done into was our auto scaling was not getting kicked in, and some of the requests were getting stopped. And even though our CPU utilization was barely 30 or 40%, but we had seen that some of the requests were getting 503, or they were basically getting dropped at the load balancer level. And the reason for that was the number of threads and workers for Puma was not configured properly. We had servers with large capacity, but the number of threads and workers were not tuned to that memory capacity basically. So we had servers like 14 GB, 18 GB, but the number of threads were very less, like 5 or 10. And it was never going to reach that level where the auto scaling will kick off. So we had to tune we had to reduce the RAM basically for the pods, and then adjust the number of threads in a such a way that it reaches that 70% memory capacity where the auto scaling will kick. I think that problem people face when they move from, say, Heroku to AWS or DigitalOcean, because Heroku behind the scenes does all of this. You just have to specify which dyno you want to use, and it will take care of most of the other things. But when you try to use the same configuration on that you had on Heroku on AWS, it may not work. So we came to know about those requests being dropped from the load balancer logs, because they were not reaching Puma. We were not able to see anything in New Relic or any of the error tracking tool. We were able to figure it out based on checking the status codes on the load balancer logs. Like, are there any 500 error codes in load balancer? If yes, then something is wrong, because the server is not accepting the requests.
I have something to share regarding an issue that I faced. If it's okay, can I share my screen?
Sure. Do I need to stop sharing?
No, we can just see this and we can continue.
No, I'm done. So no, to share your screen, do I need to stop sharing my screen?
Likely.
I think
I have to be a host for doing that.
I have stopped sharing.
Go ahead, Anubhav.
Host disabled attendee screen share. So I need to be a host.
I'm not able to hear you.
So
I think you need to make him a co-host or a host so that he can share screen.
Okay.
Or you can just allow screen sharing for members. I think there's a setting in meeting settings.
Yeah, I'm looking at it. Advanced sharing. All right. Anybody can start sharing.
So able to see the screen?
Yes.
Yeah. So the issue I was facing was that I was using this the REST client gem, and for this URL I was getting this timeout error. And when I was using using this URL on Chrome or something, then it would go. But and for the people on my team, this client was like working fine, but for my machine it was not working. So that is some error, weird error. So I tried using a different Ruby versions. This is 2.6 and this is 2.7. No, so this like open time out error. For Google, it was going on. Like, so what may be the reason that it is something, or what can be the probable thing that I should do to see what is the issue? Any idea? Any ideas? If I'm able to explain it clearly.
It's something related to your ISP.
But using Google, like Google Chrome, I was able to use this request, and I was getting a response.
Yeah, but sometimes they block based on the user agent, right? Like the REST client gem will use different user agent.
Okay.
Yeah, so set the user agent to the same as what Chrome sets using HTTP header.
Yeah, if you want to know, just hit it via Postman, grab the user agent, what Postman uses, probably that should also work.
So going down into the layers, what I used debug to see where it was blocking. So the error was happening at the TCP socket dot new. That was actually the connect callback, to connect step of the socket. So any ideas that why was this, like it was timing out there? So any reasons of that? Like,
And timeout typically occurs when the server refuses to respond. So there are multiple, like client cannot tell whether the server refused the connection or whether the server is not available. There's no distinguish. There's no distinguishing between those two. So it's quite possible that the server may have read whatever you sent, or in this case, without looking at more data, it's hard to conclude.
Does the call request work?
Sorry?
If you call this, it works or not? I don't know.
For other people on my team, it was working on their laptop.
Yeah.
It is just my laptop is not working.
Does it work when you do the call request?
That's what I was asking. Like when you just do call -x get and the API, it should return something.
So it is not returning something. It is just this is the thing. I can do this right now.
If you do want to debug this, right? Like how does somebody even start figuring out what the problem is? What you could do is, instead of using REST client or HTTP, like maybe open a socket directly on port 80 and see what low level things you're facing.
Like
are you getting ping response, etc.?
Okay. I'll do that. But this is the thing I was facing, so I'll just broke it down and see what is happening. Thank you.
Okay, so do we have any other questions? All right. So I have a question. So this is the feedback form about the meetup. So I request everyone to just fill it up so that we can plan the next meetup according to the responses. Like we can see if there is a question about what topics you want to hear. So based on that, we can have certain topics or speakers for next month's meetup. So please fill it. Anyone wants to do a lightning talk for 2 minutes? That we do in every meetup. Right. I think it's time for tea or coffee or anything else that you prefer.
Dinner.
Yeah.
Yeah.
Breakfast for me.
Okay. All right then. Thanks everyone for attending the meetup. It was really good. Thank you, Swanand and Aditya, for taking time and giving an awesome talk. Also, I'll try to put a list of resources that were mentioned during the talks on the meetup page. So we can have a list of books or blogs or gems on there on the meetup page. And next meetup we'll try to plan within 2-3 weeks, but we need some speakers and some topics. We have like it is very hard to get speakers every time, and I would really appreciate if new people starts giving talk. uh, there is no restriction on any of the topic, or there is no restriction such that you have to be a experienced speaker to give talks. Meetup is really a place to start giving talks and practicing. So please suggest your name or your friend's name for giving talks or topics, and then we can have you as a speaker next time. So that's all from my side. Swanand or Aditya, do you want to add anything?
One more thing, people have been asking about like real world implications and why this topic, or like what are the some real world examples, etc. Like maybe a lot of people are sort of concerned, or they want to understand how this boils into everyday programming. Honestly, the answer is it doesn't. Like you can go your entire Rails programming career and not ever have to deal with sockets. But like if you want to be a well-rounded engineer, foundations are important, and network programming and socket understanding of sockets is right there at fundamentals. It's as important as understanding threads and other parallelism and concurrency concepts as Aditya spoke about. So like from a being vested in your career perspective, understanding sockets and different design choices is very important. But like I said, like if you are only concerned about is it going to help me write better code, then it's not. That's the long and short of it. It'll help you like the socket or even threading and concurrency understanding. They come into play when you run into corner cases, like what Anubhav showed, for example. When you run into problems and you want to debug it, that's when these kind of little things play a part.
Yeah, I relate
Like
that.
often when we are writing code, often trial and error works. You just write something and keep changing it until it works. That approach doesn't work when you are staring in the face of a production problem. You can't just try out things, or often you can't. That is when like the understanding of fundamental pieces helps. So if not for everyday programming, understand the fundamentals for your own betterment.
So there's a old Chinese proverb: to understand why something is not working, you need an understanding of why it should be working in the first place.
Yeah, just want to share something if I can.
Go ahead.
Yeah, so like recently there was a like on the that DHS quoted about rail May of rail what the fuck. So I was discovering that most of the hottest topics were about Rails new being an interactive interface. Like uh, by it should like when we run Rails new, then it should give some interactive options to select that we can choose, because every time I was reading through it and observed that people were saying that after running Rails they were wanting, they remember that they didn't want the SQLite but they wanted to post it and they forgot to activate that flag and something like that. So one was this thing, and other was about the ARL gem. So in the past people were using ARL gem a lot, but Then it was made a public private API for active records. And like there were some issues on that, and it was that contributions for that were not accepted. So it was discussed that it would be like made public, and contributions for that should be accepted. So just wanted to share that thing with you.
Actually, we can have such a session next week or next week. Like we can discuss all the weird issues that people are facing when they're just starting with Rails, or we can just note them down and try to see if we can solve some of them.
Not a bad idea. I like the idea.
Yeah, so do I. Happy to help.
Yeah, great. Yeah, so I think that's it. Thank you all for attending, and see you next time. Thank you. Bye.
Thanks.
Thank you.
Bye.
Thank you. Thank you.
Bye everyone.
Thank you. Bye bye.